If 3I Atlas were just a comet, this video would already be over. Ice, dust, sunlight, a tail, case closed. But that is not what the data shows. 3I Atlas brightened when it should have faded. It accelerated when it should have stabilized. Its color shifted the wrong way. Its gases do not match expectations, and its motion refuses to fit inside our comet models. Our entire framework for comet physics is built on thousands of inner solar system objects. Interstellar objects, we have only 3. When the sample size is 3, certainty becomes a statistical illusion. So what happens when the evidence begins to slip beyond the frame? What we still don't understand about 3I, Atlas may not just redefine one object. It may expose the limits of the models we trust. And tonight, we follow the anomalies. When 3I Atlas was first observed displaying a visible coma and measurable gas emission, the classification followed almost automatically. In planetary science, a diffuse envelope of dust and volatiles surrounding a nucleus has long been the operational definition of a comet. The presence of sublimating material is treated as sufficient evidence. Yet this definition describes appearance, not mechanism. It tells us what we see, not how the object is fundamentally built. Our framework for comets was not built from a handful of anomalies. It was constructed from roughly 4,000 objects observed within the solar system over decades of surveys. Space telescopes, ground-based observatories, and missions such as Rosetta provided a statistical backbone. From that sample emerged typical activity curves, common, volatile compositions, and expected responses to solar heating. This internal population shaped our expectations of what a comet should be. Interstellar visitors stand in sharp contrast. ʻOumuamua, Borisov, and now Atlas constitute the entire dataset. 3 objects, each observed under different geometries, different detection limits, and limited time windows. From a statistical perspective, this is not a population. It is a glimpse. Any pattern we perceive may simply be noise shaped by selection effects. When the sample size falls below 10, statistical intuition becomes unreliable. A single extreme case can distort the apparent average. A shared feature between 2 objects can be coincidence rather than law. In such regimes, standards begin to masquerade as certainty. What appears typical may be nothing more than repetition within scarcity. Atlas exhibits a coma. Therefore, it is labeled a comet. But this conclusion arises partly because no alternative framework exists. We do not yet possess a classification system tailored to interstellar small bodies. In the absence of such a framework, we default to the closest known category. The label reflects methodological limitation more than ontological certainty. The deeper issue is not whether Atlas behaves like a comet. In some respects, it clearly does. The question is whether similarity in surface activity implies similarity in internal structure. Cometary behavior can emerge from icy conglomerates formed in our protoplanetary disk. It might also emerge from bodies assembled under different temperatures, pressures, and chemical histories in another stellar nursery. Without probing the interior, the distinction remains open. In science, categories are tools, not truths. They help organize observations so that models can be tested and refined. But when the data domain expands beyond the environment in which those categories were forged, tension appears. Atlas may be comfortably placed within the comet box for now. Yet the box itself was designed without interstellar input. This is not a failure of astronomy. It is a natural stage in encountering something rare. Every new regime begins with approximation. The caution lies in remembering that approximation is provisional. If our classification rests on a statistically fragile foundation, then some aspects of Atlas may already be stretching beyond it. The question is quiet but profound. If the framework itself emerges from scarcity, which pieces of the data are already trying to tell us that it is too small? In classical comet physics, perihelion is expected to be the moment of maximum transformation. As a nucleus approaches the Sun, solar radiation intensifies rapidly. Surface ices absorb energy, sublimate, and release gas and dust into space. Across thousands of observed comets in our solar system, this pattern repeats with remarkable consistency. Activity typically peaks within roughly 10 to 20 days of perihelion, sometimes slightly before, sometimes slightly after, but rarely far removed from it. The reason lies in the balance between incoming solar flux and thermal diffusion. Solar energy decreases with the square of distance. At perihelion, the energy input is maximal. Although heat can propagate inward through porous material, the penetration depth over a single orbital passage is limited. Most thermal models predict only shallow diffusion fronts and short response delays. In practical terms, the nucleus reacts quickly to changing sunlight. Atlas did not conform to this expectation. Observations indicate that its activity intensified well after perihelion had already passed. Instead of declining as solar input weakened, gas emission and brightness continued to rise for several tens of days. This is not a minor asymmetry. It represents a significant temporal displacement from the classical response curve derived from inner system comets. Standard heat conduction models struggle to reproduce such an extended delay. For a nucleus only a few kilometers across, the timescale for meaningful energy transport into deeper layers is relatively short. Even allowing for low thermal conductivity and high porosity, most simulations limit peak displacement to days rather than weeks. To sustain strong outgassing so long after maximum solar exposure suggests either unusual internal layering or a structural property not commonly observed. One hypothesis is that volatile reservoirs are buried deeper beneath an insulating mantle. In this scenario, solar heating gradually migrates inward, eventually reaching pockets of carbon monoxide or carbon dioxide that were previously stable. Once activated, these volatiles could drive enhanced activity even as the surface cools. Yet the magnitude and timing must still be reconciled with the decreasing energy supply. The Sun does not reverse its intensity after perihelion. Another possibility is that structural stress accumulated near perihelion and only later triggered fracturing. Microfractures could expose fresh, volatile, rich material, effectively resetting the active surface area. In this view, perihelion supplies the energy, but the mechanical response is delayed. The brightness increase would then reflect structural evolution rather than direct thermal equilibrium. What remains clear is that no standard comet model was designed around persistent post-perihelion amplification of this scale. The empirical template derived from thousands of inner system bodies does not fully encompass this behavior. Atlas appears to occupy a regime where the timing of energy release decouples from the timing of maximum solar input. This divergence forces a careful distinction between observation and interpretation. We observe increasing brightness and gas production. We infer heating as the driver. But inference depends on precedent. If Atlas formed in a different stellar environment, its internal architecture may not respond to sunlight in ways we consider typical. perihelion was expected to be the climax. Instead, it became a prelude. And that subtle shift in timing opens a deeper question. If heat alone does not dictate the rhythm of Atlas, then what mechanism is truly orchestrating its delayed awakening? In cometary astronomy, changes in brightness are expected. Es volatile isis sublimate. Dust is lifted from the nucleus and reflects sunlight, increasing apparent magnitude. Yet these changes usually follow a predictable energy logic. The amount of brightening is constrained by solar input, surface area, and volatile abundance. Atlas, however, displayed a surge that strained this logic. Observations indicate that its brightness increased by roughly 300 to 400 times within a relatively short interval. On a logarithmic magnitude scale, this corresponds to a dramatic shift, not a subtle fluctuation. Such amplification implies either a rapid expansion of reflective surface area or a substantial increase in gas and dust production. Both possibilities demand an energy source. For a nucleus estimated to be only a few kilometers across, the available solar power can be approximated. The energy intercepted is limited by geometric cross-section, even assuming efficient sublimation and dust entrainment. There is a ceiling to how much material can be mobilized purely by sunlight to sustain a several hundred-fold increase in brightness. The mass loss rate must rise sharply. The numbers begin to stretch conventional thermal balance calculations. Historical comparison deepens the puzzle. Comet Hale-Bopp, one of the most active comets ever recorded, underwent strong brightening before perihelion. Its increase followed the expected curve of rising solar flux. Energy input and activity tracked together. Atlas, in contrast, intensified when the sun's influence was already diminishing along its outbound trajectory. This reversal matters. If brightness is primarily surface-controlled, then it should correlate closely with incident radiation. As heliocentric distance increases, sublimation rates should taper. Yet, Atlas brightened when classical expectation predicted stabilization or decline. The implication is not that sunlight ceased to matter, but that it may not have been the sole regulator. One scenario involves delayed exposure of volatile, rich layers. Structural failure or fracturing could abruptly increase active area, multiplying dust production without a corresponding rise in solar energy. In such a case, the sun provides the baseline heat, but internal evolution controls the release. The brightness jump would then reflect geometry and structure rather than raw irradiance. Another possibility considers chemical energy stored in unstable compounds. If certain materials undergo phase transitions or crystallization events when reaching threshold temperatures, latent heat release could amplify activity. Such processes are discussed in models of amorphous ice transforming into crystalline ice, liberating trapped gases. Whether this mechanism alone can account for a several hundred-fold increase remains uncertain. What becomes difficult to maintain is the simplifying assumption that surface illumination alone governs brightness evolution. Atlas suggests a more complex interplay between irradiation, internal composition, and structural change. The data indicate a system capable of rapid amplification beyond what steady solar heating would predict. This does not imply exotic physics. It implies incomplete modeling. When a body formed under unknown stellar conditions enters our observational domain, it may express stored energy in unfamiliar ways. The challenge lies in distinguishing between enhanced but natural processes and mechanisms that require new theoretical treatment. The brightening event, therefore, is not merely a spectacle. It is an accounting problem. Energy must come from somewhere. If not from increased sunlight at the surface, then from deeper reserves or internal transitions. And that question lingers quietly. If the surface is not the sole driver of luminosity, then where exactly is the additional energy emerging from within Atlas? In cometary spectroscopy, color is not aesthetic. It is diagnostic. The way reflected and emitted light distributes across wavelengths reveals composition, grain size, and excitation processes. For most inner solar system comets, increasing solar heating tends to produce a redder spectral slope in reflected light. As dust dominates the coma and complex organics are exposed, scattering favors longer wavelengths. The overall appearance shifts subtly toward red as activity intensifies. Atlas did not follow this expectation. Instead of gradually reddening as thermal input increased, its observed color evolution moved in the opposite direction. The coma shifted from red tones to green, and later toward blue. This is not a subtle variation in slope. It is a directional reversal that signals a change in dominant emission mechanisms. The appearance of green is particularly informative. In cometary spectra, a strong green emission line is commonly associated with diatomic carbon, known as C2. This molecule emits prominently in the visible range when excited by solar ultraviolet radiation. The detection of C2 suggests active photochemistry and the presence of carbon-rich precursors. Green light in a coma is therefore not merely reflection. It is emission from specific molecular transitions. The later shift toward blue introduces an additional layer of complexity. Blue emission in cometary environments can arise from ionized species or from smaller dust grains that scatter shorter wavelengths more efficiently. However, sustaining strong blue signatures generally requires higher excitation energies. This implies either intensified ultraviolet interaction or a compositional transition that favors different molecular species. What makes this sequence unusual is its ordering. Under a simple model of steady heating, one would expect progressive exposure of organics and dust, leading to gradual reddening. Instead, Atlas transitioned from red to green to blue. Such a progression does not map cleanly onto a monotonic temperature increase. It suggests evolving chemistry rather than uniform warming. One interpretation is stratification. If the nucleus contains chemically distinct layers, initial activity may expose dust rich in complex organics, producing a red slope. As sublimation penetrates deeper, volatile carbon species could dominate emission, generating green signatures. Further evolution might release ions or finer particles, enhancing blue wavelengths. In this view, color becomes a vertical probe into internal structure. Another possibility involves changes in grain size distribution. Larger dust grains tend to scatter red light more efficiently, while smaller particles enhance blue scattering. A fragmentation event within the coma could shift the size spectrum rapidly, altering observed color without requiring drastic compositional change. Yet this explanation must still account for the molecular emission features associated with C2. The broader implication is that color evolution is tracing more than temperature. It reflects excitation physics, chemical inventory, and possibly structural transitions within the nucleus. A steady thermal ramp cannot easily produce a red to green to blue sequence without invoking layered composition or dynamic processing. Spectra are often described as fingerprints. In this case, the fingerprint appears to change over time. Each shift in dominant wavelength hints at material previously hidden from view. The implication that follows is quiet but profound. If the light itself is changing character, what story is it telling about the layers and chemistry concealed within Atlas? When we analyze a comet, gas composition often tells a deeper story than dust. Dust reflects light, but gas reveals chemistry. In most inner solar system comets, water vapor dominates activity once the object approaches the sun. Water ice sublimates efficiently inside a few astronomical units, and its spectral signatures become the primary driver of coma structure. Other volatiles may be present, but water usually defines the rhythm. Carbon dioxide behaves differently. It sublimates at lower temperatures than water, but is often depleted in comets that have undergone repeated solar passages. In many observed cases, CO2-driven activity peaks earlier in the inbound trajectory and becomes difficult to detect closer to perihelion because near-surface reservoirs have already been exhausted. As a result, strong CO2 emission is not typically dominant after closest approach. Atlas challenges this expectation. Spectroscopic measurements indicate pronounced CO2 signatures even after perihelion. Instead of fading, carbon dioxide appears to remain a significant driver of activity. This persistence suggests either an unusually large reservoir or a release mechanism that differs from the gradual depletion seen in typical inner system comets. Even more striking is the inferred ratio between CO2 and water. In many solar system comets, water dominates once heating intensifies. Atlas appears to exhibit an elevated CO2 to H2O ratio compared to that expectation. Such a ratio points toward formation conditions where carbon-bearing volatiles were either more abundant or more effectively trapped within the nucleus. The early and persistent appearance of CN adds another dimension. Cyanogen radicals often emerge as byproducts of photodissociation of more complex parent molecules. Their presence is common, but timing matters. Detecting CN early and maintaining it over extended intervals implies a stable and ongoing source of nitrogen-bearing compounds. This consistency hints at a chemical inventory that may not align perfectly with inner solar system norms. Chemical ratios are not arbitrary. They encode formation temperature, pressure, and radiation environment. In colder protoplanetary disks, carbon monoxide and carbon dioxide can freeze efficiently onto grains, becoming incorporated into planetesimals. If Atlas formed in a region with lower ambient temperature or different pressure gradients, its volatile inventory could reflect those conditions. Another factor involves evolutionary history. Comets native to our solar system may have lost a fraction of their more volatile components during repeated perihelion passages. An interstellar body entering for the first time would not share that thermal history. Its volatile distribution might therefore appear unusually pristine relative to our expectations. Yet, caution is necessary. Detection sensitivity, instrumental limits, and observational geometry all influence inferred abundances. We measure emission lines and translate them into production rates using models that assume certain excitation conditions. If those assumptions differ for Atlas, ratios may shift accordingly. Interpretation must remain careful. Still, the pattern is suggestive. Persistent CO2, elevated carbon relative to water, and stable CN emission together imply a volatile chemistry that does not neatly mirror the average inner solar system comet. It may reflect colder formation zones, distinct disk chemistry, or alternative trapping mechanisms within icy grains. Gas composition is a memory. It preserves conditions long vanished. If Atlas indeed carries a volatile signature shaped in another stellar system, then its coma is not merely an atmospheric envelope. It is a chemical archive. And this leads to a careful but profound question. Does Atlas carry within its escaping gases the chemistry of a star we have never seen? Gravity is usually the dominant force shaping a comet's path. Once an orbit is calculated, future positions can be predicted with extraordinary precision. Yet comets are not inert stones. As volatile gases escape from their surfaces, they act like tiny thrusters, producing measurable deviations from purely gravitational motion. This phenomenon is known as non-gravitational acceleration. For Atlas, the measured magnitude of this acceleration lies roughly between 10 to the -7 and 10 to the -6 meters per second squared. These numbers appear small, but over time they accumulate. At such levels, the position of the object can shift by hundreds of kilometers per day relative to a purely gravitational prediction. In orbital mechanics, that is significant. The physical explanation for such acceleration is typically asymmetric outgassing. If jets release material more strongly in one direction, momentum conservation pushes the nucleus the opposite way. The Marsden formalism, widely used in cometary dynamics, parameterizes this effect as a function of heliocentric distance. It assumes that outgassing strength tracks solar heating in a predictable manner. In the case of Borisov, non-gravitational acceleration was detected but aligned broadly with expectations. Its strength was modest and appeared during phases of active sublimation. The timing corresponded reasonably well with peak gas production. There was tension, but not contradiction. Atlas presents a more difficult picture. The measured acceleration becomes prominent at a stage when classical models predict declining outgassing. By that point in its trajectory, solar flux is decreasing and volatile activity should be tapering. Yet the dynamical signal strengthens rather than fades. The thrust appears late, not early. This mismatch challenges the core assumption embedded in the Marsden model. If acceleration scales with instantaneous solar heating, then it should follow a similar temporal profile. A delayed increase implies either that the gas production curve itself is delayed, or that the force mechanism is not purely tied to surface sublimation as normally parameterized. One explanation could involve deeper, volatile pockets that become active only after sufficient heat penetration. If these reservoirs are anisotropically distributed, they might produce sustained thrust even as the surface cools. However, such a scenario must still reconcile the magnitude of acceleration with the estimated mass loss rates derived from observed brightness. Another possibility considers the geometry of jets. If a limited number of active vents maintain a stable orientation relative to the spin axis, the resulting thrust vector could remain coherent over extended periods. Such directional stability would amplify cumulative orbital deviation. Yet this requires structural rigidity and internal organization that may not be typical for loosely bound cometary nuclei. What remains uncertain is whether the observed acceleration can be fully accounted for by gas momentum alone. To evaluate this, one must compare the required thrust to the measured production rates of volatiles. If the necessary mass flux exceeds observational constraints, then additional mechanisms may need consideration. At present, that accounting is still under refinement. Non-gravitational acceleration is subtle. It does not announce itself dramatically. It reveals itself in residuals, in small discrepancies between predicted and observed positions. Yet these discrepancies accumulate, and they point to forces operating beyond gravity. In Atlas, the timing of that force is the central tension. It strengthens when standard sublimation physics suggests weakening. This does not invalidate the comet model, but it stretches it. And so a deeper uncertainty remains. If the thrust does not simply mirror sunlight, then what is the true engine behind this late acceleration? In orbital mechanics, small deviations matter. When astronomers calculate a comet's trajectory, they first model gravitational influences from the Sun and planets. Any remaining discrepancy between prediction and observation appears as a residual. In active comets, such residuals are often attributed to non-gravitational acceleration caused by asymmetric outgassing. But the direction of that acceleration is just as important as its magnitude. For many comets, the thrust vector varies over time. As the nucleus rotates, different active regions rotate into sunlight. Jets strengthen and weaken depending on illumination geometry. The resulting acceleration fluctuates accordingly, sometimes even reversing components over a rotation cycle. This variability reflects the chaotic and uneven nature of surface activity. Atlas appears different. The measured deviation from a purely gravitational orbit indicates a vector that maintains a relatively stable orientation over extended periods. Instead of oscillating with the estimated 16-hour rotation, the acceleration seems to preserve direction. The residuals do not smear randomly in phase with spin. They align. This alignment implies that the source of thrust is not evenly distributed across the surface. A symmetric distribution of vents would average out over rotation, producing limited net acceleration. To maintain a coherent vector, activity must be biased towards specific regions. The asymmetry must persist across multiple rotation cycles. One explanation is geometric. If the dominant jets are located near the rotational pole, their orientation relative to space changes little as the body spins. In such a configuration, thrust remains directionally stable. However, maintaining multiple coherent jets in such alignment requires structural and compositional organization. It is not typical of loosely aggregated cometary nuclei. Another possibility is deeper channeling of gas flow. If internal conduits constrain outgassing through narrow vents, the emerging jets may remain fixed in orientation relative to the internal structure rather than the transient surface. This would couple mechanical integrity to dynamical behavior. The architecture of the core would directly shape the motion through space. What makes this particularly significant is statistical expectation. Natural cometary activity is often irregular. Erosion alters vent geometry. Outbursts change local topography. Over time, the thrust vector tends to drift. Sustained directional stability is comparatively rare. When observed, it forces dynamical models to account for unusual persistence. The data do not imply control in any deliberate sense. They imply constraint. Motion that appears orderly suggests underlying structure that channels energy in a preferred direction. In dynamical terms, the comet behaves less like a randomly venting aggregate and more like a system with internal coherence. Such coherence complicates simplified models that assume isotropic or weakly anisotropic sublimation. If thrust maintains a stable vector beyond what rotational averaging predicts, then the internal configuration must be reconsidered. Structure, composition, and rotation state become inseparable variables. Atlas therefore presents not just acceleration, but directionality that persists. It is this persistence that causes several existing models to hesitate. because once motion ceases to look random, it hints at deeper order, and that order raises a fundamental limit. How structured can a natural object become while still being considered an ordinary comet? When a comet becomes active, gas does not escape uniformly. It vents through localized regions where volatile material is exposed. These vents generate jets, narrow streams of dust and gas that project into space. In most observed comets, these jets are dynamic and unstable. As the nucleus rotates, the jets sweep through space, tracing curved or spiral patterns in the coma. Over time, the structure appears blurred or smeared by rotation. Atlas presented something more structured. Imaging revealed at least 7 distinct jets emerging from its nucleus. They were not diffuse outflows blending into one another. They appeared as separate, coherent features with identifiable geometry. The number alone is notable, but the persistence of their shape is even more significant. The estimated rotation period of Atlas is approximately 16 hours. For a body rotating on that timescale, any surface vent should trace a sweeping arc across the coma within a fraction of a day. Over several hours, the projected jet would be expected to curve noticeably, producing a spiral-like morphology. This behavior is commonly documented in well-studied comets. Yet in Atlas, the jets maintained a stable orientation over extended intervals. Instead of smearing into arcs, they retained relatively fixed geometry for many hours. This implies either that the source regions are aligned closely with the rotational axis, minimizing apparent sweep, or that the venting originates from deeper, collimated channels that constrain outflow direction. If the jets are aligned with the spin axis, the geometry becomes less sensitive to rotation. A polar vent would project outward with minimal lateral displacement as the nucleus turns. However, maintaining multiple distinct polar-aligned vents requires internal structural organization. Such symmetry is not impossible, but it is uncommon. The alternative is mechanical rigidity. If Atlas possesses a more consolidated or partially sintered interior, fractures could form narrow conduits that channel gas efficiently. Deep vents would act like nozzles, focusing flow into coherent streams rather than diffuse plumes. This would preserve jet sharpness even as rotation proceeds. Such behavior is rare among loosely bound cometary nuclei, which are often described as rubble piles held together by weak gravity and fragile cohesion. In those bodies, vents evolve rapidly, collapse, or migrate as material erodes. Persistent, well-defined jets over multiple rotation cycles suggest either unusually stable topography or compositional gradients that reinforce structural integrity. Jet morphology also feeds directly into dynamical effects. If outflows are confined and directional, they generate more coherent thrust vectors. This connects structural geometry to orbital deviation. The physical architecture of the nucleus becomes dynamically relevant, not merely visually interesting. In Atlas, the refusal of jets to smear under rotation suggests internal organization beyond the average comet template derived from inner solar system bodies. Whether that organization reflects deeper volatile layers, enhanced mechanical strength, or unfamiliar formation conditions remains uncertain. Structure leaves signatures in motion and light. When jets behave in ways that resist rotational smearing, they quietly point inward, toward the nucleus itself. And that inward direction leads to a deeper consideration. If Atlas can sustain such stable venting geometry, What does that reveal about the architecture hidden beneath its surface? Jets are localized. A tail is global. In most comets, jets feed the larger coma, and from that diffuse cloud, solar radiation pressure and the solar wind sculpt a tail that stretches millions of kilometers. The process is gradual. Dust is released. Sunlight pushes it outward. And over time, a coherent tail forms. The scale is immense. But the buildup is usually progressive. Atlas produced a tail approaching 3 million kilometers in length. That scale alone is not unprecedented. What distinguishes this case is the speed of morphological change. Observations indicate that the tail's structure evolved significantly in less than 24 hours. For an object at astronomical distances, such rapid transformation demands an explanation rooted in dynamics and energy transfer. To stretch material millions of kilometers within a day requires substantial ejection velocities. Dust grains must leave the nucleus at speeds high enough to populate distant regions quickly, while still remaining gravitationally unbound. The higher the initial velocity, the more abrupt the apparent extension of the tail. These speeds, inferred from modeling, appear elevated compared with many typical inner system comets. Solar radiation pressure alone cannot instantaneously reorganize a coma into a sharply extended structure. Radiation acts continuously but relatively gently. Its influence scales with particle size and distance. A dramatic shift in tail geometry over a single day suggests that a large quantity of material was injected into the coma in a short burst, rather than redistributed slowly by sunlight. This distinction matters because it shifts the emphasis from sculpting to supply. The sun can shape what is already there, but it cannot create mass. If the tail lengthens dramatically, the source must be an increase in production rate. That production must be energetic enough to accelerate particles outward rapidly. The question becomes not how the tail is shaped, but how the material is launched. Surface sublimation is typically limited by the energy flux received per unit area. There is an upper bound to how much gas and dust can be driven off by steady heating. When observed activity exceeds what that flux can plausibly sustain, alternative processes must be considered. One possibility is that subsurface pressure built up beneath an insulating crust, eventually rupturing and releasing material explosively. Such internal release mechanisms would naturally produce higher ejection velocities. Gas confined within porous layers can accelerate as it escapes through narrow fractures, functioning briefly like a nozzle. The resulting dust entrainment could seed the coma with particles already moving at significant speeds. Radiation pressure would then extend these particles into a rapidly growing tail. The rapid morphological change suggests that the nucleus is not merely passively heated. It appears capable of storing energy or pressure and releasing it episodically. This behavior aligns with the idea of structural complexity beneath the surface, perhaps involving layered volatiles or mechanically strong crusts that trap gases until thresholds are crossed. In this context, the tail becomes more than a passive feature shaped by the sun. It becomes a dynamic indicator of internal processes. A 3 million kilometer extension forming or reorganizing within a day is a visible manifestation of hidden energy transfer inside the nucleus. Comet tails are often described as delicate and ephemeral. In Atlas, delicacy coexists with sudden intensity. The scale suggests power, while the speed suggests stored potential. And this convergence leads to a deeper reflection. If material can be liberated so rapidly and on such scale, what internal mechanism is capable of driving that release? Most comet tails extend away from the sun. This geometry is not arbitrary. Solar radiation pressure pushes dust particles outward, while the solar wind shapes ionized gas into a separate, often straighter, ion tail. Under normal circumstances, both structures align broadly, anti-solar and anti-tail. However, appears to defy this expectation. It seems to point toward the sun, creating the visual impression of material moving in the wrong direction. In reality, an anti-tail is a projection effect. It forms when Earth crosses the comet's orbital plane and observes dust distributed along that plane edge-on. Under very specific geometric conditions, particles that were released earlier and now lie along the orbital path become visible as a spike, apparently pointing sunward. The phenomenon is delicate and depends on particle size, distribution, and orbital alignment. For an anti-tail to appear sharply defined, the dust particles must occupy a relatively thin and coherent sheet along the orbital plane. If particle velocities vary too widely, or if solar wind and radiation pressure disperse them excessively, the structure becomes diffuse and indistinct. Precision in particle size and ejection timing is essential. Atlas displayed an anti-tail under conditions of relatively strong solar wind activity. Plasma interactions near the sun can distort ion structures and accelerate charged particles unpredictably. In such an environment, one might expect fragile dust alignments to degrade rapidly. Yet the anti-tail persisted with surprising clarity. This persistence introduces tension with standard plasma interaction models. Those models account for the behavior of ionized gas fairly well. But dust dynamics are influenced by a combination of gravity, radiation pressure, and electromagnetic forces. When solar wind conditions intensify, small particles, especially, should be susceptible to disruption. The maintenance of a coherent anti-tail implies either particle sizes larger than assumed or a distribution tightly constrained in velocity space. If particles are larger, radiation pressure affects them less dramatically, allowing them to remain close to the orbital plane. However, larger particles are typically ejected at lower velocities and may not populate distant regions rapidly. If instead the ejection velocities were finely tuned, the resulting dust sheet could remain thin even under moderate perturbation. Both scenarios require conditions that are not commonplace. Another possibility involves episodic release. If a burst of material was emitted within a narrow time window, particles would share similar orbital parameters. Such coherence would enhance the visibility of an anti-tail when geometry aligns. This links the phenomenon to internal activity patterns rather than purely external shaping forces. The anti-tail therefore becomes more than a visual curiosity. It becomes a diagnostic constraint. Any successful physical model of Atlas must account not only for jets, brightness, and acceleration, but also for the survival of a geometrically delicate dust sheet under active solar conditions. Plasma models can simulate ion tails with impressive accuracy. Yet the dust component introduces nonlinear complexity, grain charging, magnetic field coupling, and variable radiation pressure combine in ways that are difficult to predict precisely. Atlas appears to maintain order where disorder might be expected. In the broader picture, the anti-tail problem highlights the interplay between geometry and physics. A thin alignment of particles must persist long enough to be seen. Forces must balance just precisely enough to avoid dispersion. When such balance occurs under strong solar influence, it invites reflection. Are our assumptions about particle distribution and plasma interaction complete? Or is there an ingredient in the system we have not yet fully considered? Comets are often described as fragile. Spacecraft missions, such as Rosetta, revealed nuclei with high porosity, low bulk density, and tensile strength barely sufficient to hold their structure together. Many are closer to loosely bound aggregates than solid monoliths. Under strong thermal stress or tidal interaction, fragmentation is not uncommon. Some comets split spontaneously as volatile pressure exceeds structural limits. As a comet approaches the Sun, thermal gradients develop between illuminated and shadowed regions. Surface layers expand while deeper layers remain cold, generating internal stress. At the same time, sublimating gases build pressure beneath insulating crusts. Plasma interactions with the solar wind further contribute to surface erosion and electrostatic charging. The combined effect can destabilize weak structures. In several observed cases, comets undergoing intense heating have fragmented into multiple pieces. Such breakups dramatically increase brightness, but also signal structural weakness. Borisov, for example, displayed indications of fragmentation and mass shedding as it traveled through the inner solar system. Its behavior was consistent with a relatively delicate internal cohesion. Atlas, by contrast, has endured substantial thermal input and plasma exposure without clear evidence of catastrophic fragmentation. Despite strong outgassing, rapid morphological changes, and measurable non-gravitational acceleration, the nucleus appears to have maintained overall integrity. No large-scale breakup has been definitively observed. This resilience raises a structural question. If internal pressures were sufficient to drive powerful jets and large-scale dust release, why did the body not fracture more dramatically? One possibility is higher bulk density. A denser nucleus would better withstand both thermal stress and internal gas expansion. Another possibility is partial lithification, where icy grains have sintered or compacted over time, increasing mechanical strength. There is also the hypothesis of compositional reinforcement. If Atlas contains a higher fraction of refractory or even metallic components mixed with volatiles, the structural framework could be more robust than typical icy rubble piles. Even a modest increase in cohesive material could significantly alter fragmentation thresholds. It is important to separate speculation from observation. We do not yet possess direct measurements of Atlas's internal density or tensile strength. What we observe is survival under stress. The absence of fragmentation does not prove metallic structure, but it does constrain possible models. Any internal configuration must be strong enough to tolerate repeated pressure cycles without catastrophic failure. The comparison with Borisov underscores this contrast. Two interstellar objects, both exposed to similar solar conditions, yet exhibiting different structural responses. Such divergence may reflect differences in formation environment, thermal history, or compositional makeup. It reminds us that interstellar bodies may not form a uniform class. Structural endurance under extreme stress is not merely a detail. It influences jet coherence, acceleration, magnitude, and tail formation. A stronger nucleus can channel gas more efficiently and resist disruptive collapse. In this sense, mechanical properties become central to interpreting the entire set of observations. Atlas has endured where many comets might have fractured. That endurance narrows the range of plausible internal architectures. Whether the answer lies in density, composition, compaction, or an unfamiliar mixture of all three remains unresolved. But the implication is unmistakable. Beneath the luminous coma, the core of Atlas may be built differently than we expect. And that leads inward once more. What at a fundamental level. Is this nucleus truly made of? Determining the size of a distant small body sounds straightforward. Measure its brightness, account for distance, and compute its diameter. In practice, the calculation depends critically on one uncertain parameter, albedo, the fraction of sunlight reflected by the surface. Without knowing how reflective Atlas truly is, any size estimate remains conditional. A darker surface reflects less light, meaning the object must be larger to produce the same observed brightness. Conversely, a highly reflective surface can appear bright even if physically small. This degeneracy between size and reflectivity is fundamental in planetary astronomy. It cannot be resolved without independent constraints, such as thermal infrared measurements that directly probe emitted heat. For Atlas, albedo is not yet tightly constrained. If one assumes a relatively dark surface similar to many cometary nuclei, the resulting diameter estimate increases substantially. Some models using lower albedo values permit sizes in the range of 8 to 10 kilometers. That would place Atlas among the larger small bodies ever detected entering from interstellar space. To appreciate this scale, comparison is helpful. ʻOumuamua, the first confirmed interstellar visitor, was estimated to measure only a few hundred meters across, roughly 100 to 400 meters depending on geometry and reflectivity assumptions. Borisov, the second, was larger but still modest, on the order of half a kilometer to 1 kilometer in diameter. If Atlas truly spans several kilometers, it exceeds both predecessors by a significant margin. In terms of volume, the difference becomes dramatic. Volume scales with the cube of radius. A body 10 times wider contains roughly 1,000 times more material. The mass difference could therefore be orders of magnitude larger than that of ʻOumuamua and Borisov. This matters dynamically. Larger bodies require more energy to eject from their home systems. They are less easily perturbed by stellar encounters and more resistant to collisional erosion during interstellar travel. If Atlas is indeed on the upper end of the size estimates, its journey may reflect formation and ejection processes involving massive planetary systems or strong gravitational interactions. Yet the uncertainty remains central. If albedo were higher than assumed, the diameter would shrink accordingly. Without precise thermal measurements, we are navigating a range rather than a point. This uncertainty propagates into density estimates, structural models, and interpretations of internal composition. Size is not an isolated parameter. It anchors many other physical inferences. A larger nucleus could help explain structural endurance under stress. Greater mass would provide stronger self-gravity, enhancing cohesion. It could also accommodate deeper, volatile reservoirs, consistent with prolonged outgassing and delayed activation. In contrast, a smaller nucleus would demand alternative explanations for the same phenomena. The size question therefore extends beyond geometry. It touches origin. If Atlas measures several kilometers across, it implies formation in a region capable of assembling substantial planetesimals and subsequently ejecting them into interstellar space. Not all stellar systems may do so efficiently. We are left with a range, not a certainty. Atlas may be modest in scale or unexpectedly large. Each possibility carries different implications for its history and for the population of interstellar objects as a whole. And that uncertainty invites reflection. If this body is truly larger than any interstellar visitor we have yet measured, what kind of stellar environment gave rise to it? Interstellar space is often described as empty. In reality, it is sparse, but not benign. A small body traveling between stars is exposed for immense stretches of time to cosmic radiation, micrometeoroid impacts, and gravitational perturbations. If Atlas originated in another stellar system, it may have wandered for hundreds of millions or even billions of years before entering ours. Survival across such timescales is not trivial. Galactic cosmic rays gradually alter the surface chemistry of exposed ices. Over long durations, irradiation can darken material, break molecular bonds, and restructure outer layers. Microscopic impacts erode surfaces grain by grain. While each interaction is minor, their cumulative effect over geological timescales becomes significant. A loosely bound nucleus might slowly weaken under such exposure. Collisions present another challenge. The Milky Way's disk contains dust clouds, interstellar remnants, and other planetesimals. Although the average density is low, over billions of years the probability of encounters rises. Even a modest collision could fracture a fragile body. The fact that Atlas appears intact suggests either resilience or statistical fortune. There is also gravitational scattering. As stars orbit the galactic center, close stellar passages can alter trajectories. Many small bodies are likely ejected into interstellar space by giant planets during the early evolution of planetary systems. Yet remaining on a stable interstellar path long enough to intersect another star system requires a sequence of orbital circumstances. The improbability compounds further. Atlas not only survived interstellar travel, it entered the inner region of our solar system at a time when wide field surveys are active and sensitive enough to detect it. For most of human history, such an object could have passed unnoticed. Detection requires alignment of trajectory, brightness, and observational capability. When viewed as a chain of events, the sequence appears extraordinarily unlikely. Formation in another system, gravitational ejection, long-term survival through radiation and collisions, a trajectory intersecting ours, and arrival during an era of advanced telescopes. Each step has a non-zero probability. But the combined probability seems small, yet low probability events occur routinely when underlying populations are large. A single lottery win appears improbable, but with millions of participants, winners emerge regularly. The same logic applies to astrophysical populations. If interstellar objects are abundant throughout the galaxy, then occasional visitors become statistically inevitable. This reframes the apparent improbability. Rather than focusing solely on the rarity of one object's journey, we must consider the unseen population drifting between stars. Current estimates of interstellar object density are uncertain and based on only a few detections. If Atlas is larger than previous visitors, it may indicate that our census underestimates both size distribution and total number. Survival, in this light, may not be exceptional but representative. Perhaps countless bodies wander the galaxy, most never intersecting our line of sight. Atlas may be one of many, revealed not because it is unique, but because our instruments are finally capable of seeing it. The tension lies between improbability and abundance. If the odds for one object seem absurdly low, the alternative explanation is a vast, unseen reservoir. And that possibility leads to a larger reflection. Are we underestimating the true density of interstellar objects moving quietly through the galaxy? By this point, Atlas presents not one anomaly, but a pattern of partial mismatches. Each physical domain offers a plausible explanation for one aspect of its behavior, yet none of them, taken alone, accounts for the whole. The difficulty is not the absence of models, it is their fragmentation. Thermal models explain delayed activation reasonably well. If heat penetrates gradually into deeper volatile layers, post-perihelion outgassing can be sustained. Variations in thermal conductivity, porosity, and layering offer mechanisms for timing shifts. But these models struggle to reproduce the magnitude and late onset of non-gravitational acceleration. The predicted thrust often falls short of observed orbital deviations. Gas dynamic models focus on asymmetric outgassing. If jets are sufficiently collimated and persistent, they can generate measurable acceleration. This framework addresses the orbital residuals more directly. Yet, it assumes that gas production tracks solar heating in a relatively smooth function of distance. In Atlas, timing and intensity do not align cleanly with that assumption. The acceleration appears when classical sublimation should be waning. Structural models introduce another dimension. A denser or partially consolidated nucleus could withstand extreme stress without fragmentation. Deep vents might channel gas in stable orientations, preserving jet coherence. This helps explain resilience and morphology. But structural strength alone does not determine spectral evolution. It does not naturally account for the transition from red to green to blue emissions or the unusual volatile ratios. Spectroscopic interpretations suggest compositional layering or unfamiliar chemistry shaped in a different stellar environment. These ideas address the color shifts and volatile abundances. Yet composition alone does not automatically generate the observed dynamical signatures. Chemistry must still translate into force through momentum exchange, and the accounting must close quantitatively. Each model therefore captures a fragment of reality. Thermal physics explains timing shifts. Gas dynamics explains thrust. Structural mechanics explains endurance. Spectroscopy explains emission behavior. But when these frameworks are applied independently, inconsistencies remain at their boundaries. The seams become visible where one domain hands off to another. This is not unusual in frontier science. When a new regime is encountered, established models often operate near the edge of their validity. They were constructed using populations shaped by similar formation histories. Atlas may belong to a different statistical family. If so, the assumptions embedded in each isolated model may require integration rather than replacement. A comprehensive framework would need to couple thermal evolution, volatile transport, mechanical strength, and jet geometry within a single dynamical simulation. It would have to reproduce brightness curves, teen spectral transitions, acceleration vectors, and structural stability simultaneously. Such synthesis is computationally demanding and conceptually complex. Until such integration exists, Atlas will continue to appear as a mosaic of partial explanations. The data do not contradict physics. They challenge compartmentalization. What we are witnessing may be less a failure of theory than a signal that our theoretical partitions are too rigid for this object. Scientific frameworks are rarely rewritten in a single moment. They evolve as anomalies accumulate and synthesis becomes unavoidable. Atlas may represent such a moment of pressure, where independent models must converge or expand, and this widens the frame of the problem. At what point does accumulating tension signal that the frame itself must be re-examined? Every scientific field is built on precedent. Cometary physics, as we practice it today, rests on thousands of objects formed within a single stellar system. Their orbits, compositions, densities, and thermal responses have shaped the equations we trust. We often forget how local that knowledge truly is. Our models were calibrated inside one planetary disk, around one star. When an interstellar object enters that framework, we instinctively compare it to what we already know. We ask which known class it most resembles. We adjust parameters, modify coefficients, and test variations. But there is a deeper possibility that is harder to confront. The object may not simply be an outlier within our model. It may originate from a chapter our model never included. The chemistry of interstellar planetesimals is not yet comprehensively mapped. We infer compositions from protoplanetary disk observations and from meteorites formed in our own system. Yet disks around other stars display wide variation in temperature gradients, elemental abundances, and radiation environments. It would be surprising if every stellar nursery produced identical small bodies. Atlas may therefore represent not a violation of cometary physics, but an expansion of it. Its volatile ratios, spectral transitions, dynamical anomalies, and structural endurance may reflect formation conditions that our solar system did not sample. If so, the data are not contradicting theory. They are extending its domain. There is a moment in scientific progress when accumulation of anomalies does not destroy a framework, but reveals its boundaries. The responsible response is not to abandon the model prematurely, nor to force the data into compliance. It is to acknowledge uncertainty with clarity. To say that we do not yet know is not a weakness. It is an honest state within the scientific method. Atlas confronts us with that humility. It reminds us that our statistical foundation for interstellar bodies consists of only a handful of detections. It reminds us that models derived from thousands of local examples may not immediately generalize across the galaxy. And it reminds us that discovery often precedes explanation. In this sense, Atlas may not be difficult because it breaks the rules. It may be difficult because it reveals how provisional those rules always were. Scientific laws emerge from patterns. When patterns broaden, laws adapt. The process is gradual, often quiet, and sometimes uncomfortable. The hardest possibility is not that Atlas is extraordinary in some exotic way. The harder possibility is that it is ordinary within a population we have barely begun to perceive. If interstellar space contains diverse families of small bodies, then our cometary taxonomy may represent only a local dialect of a much larger language. That realization does not diminish what we know. It reframes it. Our understanding of comets remains valid within its domain. Atlas simply hints that the domain may be narrower than the galaxy itself, and that widening horizon carries both uncertainty and opportunity. If a single interstellar object can expose the limits of our assumptions, then the broader population drifting unseen between stars may hold even deeper revisions. The galaxy is vast, and we have sampled only a fraction of its small bodies. Atlas is one data point, but it points outward, and so we arrive at the quietest and most demanding possibility. If one visitor can stretch our framework, how many unseen chapters remain written across the galaxy, waiting for the moment when we are finally able to read them? Atlas may eventually fit into a refined model. Its chemistry may be explained, its acceleration quantified, its structure simulated in detail. Over time, what feels uncertain today may become textbook knowledge. But there is something quietly valuable about this moment before resolution. Right now, Atlas exists at the boundary between data and understanding. We can measure its light. We can trace its orbit. We can model its gas. And yet, when we place all the pieces together, a complete picture still resists us. That resistance is not a flaw in science. It is science working exactly as it should. Every time we encounter something that does not sit comfortably inside our existing framework, we are given a choice. We can force the anomaly to conform, or we can allow it to expand the frame. Atlas reminds us that our knowledge of comets is rooted in one star system, one chemical history, one planetary architecture. The galaxy, however, contains hundreds of billions of stars, each with its own disk, each with its own conditions, each potentially producing bodies unlike anything we have seen before. If a single interstellar visitor can stretch our assumptions this far, then what might 100 reveal? How many different kinds of small worlds drift between the stars, carrying chemistries and structures that do not resemble our own? And how many chapters of planetary physics remain unwritten? Simply because we have not yet encountered the right object. We are only beginning to survey the sky with the sensitivity required to find these wanderers. In the coming decades, new observatories will expand that census dramatically. Atlas may not remain an exception. It may become the first hint of a much larger population. Until then, we are left with something both humbling and exciting. A reminder that the universe is not obligated to fit inside our current models, and that sometimes the most important discoveries are the ones that quietly reveal how much more there is to learn. If you would like to continue exploring questions like this, where observation meets uncertainty and data pushes the boundaries of theory, consider subscribing to the channel, because the galaxy is vast, and we are only just beginning to read it. Thank you for watching.